Alright guys, today we're going to look at the very first problem under the DFS pattern. In the previous video we looked at the DFS intro, how recursion works, and how we can establish a simple DFS template that can be reused in similar problems. Now in this case we have a binary tree, and then we need to find its max depth. Now as the name suggests, max depth is the longest root to leaf path. So let's get started. Let's say this is the question that this is all the interviewer gives you in an interview setting. And with this information, you need to first understand it, make sure you communicate with the interviewer to inform them that you understood it, type out some pseudocode, and then eventually code the function out. Right? And this is how I would proceed. So looking at this information, it says given a binary tree, so we know how a binary tree looks like and what the conditions are, and then find its max depth. We are also given the definition for the max depth. So let's assume we have this binary tree, and binary tree would mean that every node will either have 0 children, 1 child, or 2 children node. And so in this case, 5 is the root node. It has 2 child nodes, 4 and 6, and 4 has 2 child nodes, 3 and 8. 6 has no child nodes at all. Any node which does not have a child node is called a leaf node. So let's define leaf node. Leaf node is node with no child nodes. Right. And everything else is a normal node. We call them non-leaf nodes. 5 is a non-leaf node because it has got more than 0 children. 4 is a non-leaf node, 6 is a leaf node, 3 is a leaf node, 8 is a leaf node. So now that we understood what a leaf node means, we can intuitively look at this binary tree and try to come up with the answer. We need to find max depth of this binary tree. What would it be? Let's see. We have got our root, and let's try to traverse the left subtree to see how many nodes there are between this root node and the leaf nodes in the tree. So we have one node, and root node itself is a node, so 1 plus 1 plus 1. Now this is the leaf node, we can't go down any further, so we record our result. We say there are 3 nodes in total from root to the first leaf node. Now let's traverse from root to the second leaf node. So we say 5, which is a node itself. So we have 1 plus 1 plus 1. 8 is a leaf node. We end there and we record our result, 3. And then finally we get to the right subtree and say, okay, we have exhausted all the nodes in the left subtree of this root node. So let's go to the right subtree now of this root node. And so 5 itself is a node, so we have 1 plus 2 plus 1 basically, which is 2. This is the leaf node, so the call ends there, so we have 2. So we had 3 leaf nodes total in the tree, and we have 3 different results, which are the lengths of paths from the root node to the respective leaf nodes. We need to return max of these results, which is 3, 3, 2, which ends up being 3. So this is what we need to do. And looking at the statement, you should kind of get an intuition about what we are going to implement. Right? Before walking through the space and time complexity, let's try to implement this function real quick. It should be a short one. Function, let's assume, let's call it max depth. We obviously know it's for tree. We're given the reference to the root of the tree, and that's a good nomenclature to use here. Every time we have to start with the root node, and then for each call, the incoming node is considered as the root node, and we go further down the line. And so it's always good practice to call the node root instead of calling it node. right? So let's always try to call it root, because from the function calls perspective, every call that's getting a node reference is the root node. It does not know what the node before it was, what the node after it is. So now that we have our function definition, let's get to our first logical step, which is to check if the root is null or not. Well, if the root is null, what do we do? Let's say for now we just return null. Right? We don't know what to do, so let's just return null. Now let's get to the core of the problem. We have a root. We need to go in to the left subtree and exploit host all the nodes in the left subtree. And so we say, let's call a function max depth by passing in root.left. And then this is going to lead to a new call. That new call is again going to call left, and so on and so forth. We also wanted to call all the nodes. We also wanted to traverse all the nodes towards the right of this root node, which is 6, right? So we have to call max depth root.right. All right. And this will cover all the left subtree nodes. This will cover all the right subtree nodes. And then finally, we need some answer, right? Return something. We need an answer here. Well, what would that be? Let's try to understand what happens when a root node becomes null. When would this condition be hit? This condition would be hit when we call our function when the previous node is a leaf node, right? So if the previous node, in this case, let's assume the root node is 3 here, right? If the root node that's being passed is 3, and we try to call root.left, right? We say 3 left node, and so the incoming node now becomes 3's left node. Now the left node is going to be null because 3 is a leaf node, and so this condition will only be hit for all the nodes that were leaf node, right? For all the calls that were originated or that were spawned by a leaf node. So if 3 calls max depth with 3.left, we're going to hit this condition and we're going to return null. Now let's look at what we actually want to return. We just don't want to return null, because null does not signify anything, and null is not going to get us to the answer that we're looking for. 3 needs to return 1, right, or 0, something. It needs to return an integer value so that we can use it while we trace back to the root node again. If 3 returns 1, we're going to trace back to the previous caller, which was 4. 4 is going to return 1. So we're going to go back to the main caller root, and root itself is 1. So we add 1 plus 1 plus 1, which is 3, right? And so what we essentially want every time is for us to return what the previous result was plus 1, right? And if the leaf node ends up returning 1, then when we trace back to the root, every node is just going to return itself plus 1. And so it would be best to return a arbitrary integer value, and probably it's going to be 0 here, because 0 signifies that the tree has ended. You have to start tracing back, right? This signifies that we need to start tracing back to the original caller. One more thing to note here is that we have 2 calls, one for the left subtree, one for the right subtree. and we want to use the results of both, right? So we can either do this, we can say result equals whatever the left subtree returns plus, let's call the right subtree, and whatever the right subtree returns, store it in the result, and then return result plus 1. Well, this is a good way of doing it. But there's even a concise way of doing it, right? We can use this statement here where we call our max depth by passing in the left node and max depth by passing in the right node. Let's just put it in one single statement and say max depth, first call the left one and then call the right one. Root.right. Okay. Now if we look at our original intuitive condition, it was about finding all the paths and then adding the depths of and then finding the max out of all the depths that we have found so far. So we need to find max, that's for sure, right? And this is what the result should be, right? This result is going to override the number with the next path's depth, and we don't want that. Let's see what's going to happen if we use this statement instead of this one. Let's assume we don't have this statement. Let's assume we're just going with this statement. Let's see what our function will return if we pass in this tree. It'll say 5, 4, 3. It's going to get 3 here, and then it's going to again get 3 for this path, 5, 4, 8. But then it's going to replace the result with 3 again. And then when it gets to the right subtree, it's going to get 2. So it's going to replace the result with 2 and then return the result, right? So if we found the flaw here, the flaw was we need to add 1 here and not here. It's just going to return result. Right? 6 is going to return 0 in this case. And there was no left subtree so far, so it's going to return 1. Now since this is not going to return at the max depth, we need max of whatever depth we achieved from all the paths in the left subtree and whatever max depth we achieved from the right subtree. We need to find the max among those two values and then eventually return plus 1. So let's get rid of this statement, which was erroneous in our case, and then let's just consider this one. And there's no need for us to store the result anymore because we know what our answer is, and that is to compare the depth that we got from the left subtree with the depth that we got from the right subtree at every node level, and then add 1 to it and return it all together. So as you can see, this is just a two-liner for this solution, and let's walk through our example tree again. We have 5, pass in as root. Well, 5 is not null, so it's not going to return anything yet. It's going to get here, it's going to say 5's left, so it's going to call it with 4, right? So the first call was 5, it's going to go here, it's going to call 4, 5's left child is 4. Now the function is going to receive 4, 4 is not null, so it's going to go in here, and then it's going to call 4.left, which is 3, so our function is going to get 3. Well, 3 is not null, so we're going to go to this statement and call 3.left, which is in fact null, right? So 3.left initiated this call, which is null. Well, root is null now. I think it would be clear for us to say what the incoming node is, and then called by 3.left. And called by 3.left. And then similarly, okay, now it's null. So what is it going to do? It's going to return 0. Right? So it's going to set this one to 0. And then it's going to move on to the next call, which is root.right. Again, it's going to say 3 is right, which is again null. There's no node below 3. Called by root.right. it's again gonna return 0. So at this point we have got max of 0 comma 0 plus 1. All the calls are complete for 3, we return 1. Right? Max of 0 comma 0 is going to give you 0, 0 plus 1 is 1, so you return 1. Right? Now you have returned 1, you're at 4 now. Right? Let's go back to 4, trace back to 4. 4 is going to return what? What 3 had already returned, which was 1. And it's going to add 1 to it and return it, which is now 2. Trace back, we have 5. 5's this statement was already checked, so we are at the very end. What did 4 return? 4 returned 2, right? So we have 2, and then we add 1 to it and return the result, which is 5. And now we're going to get to 5, and then we're going to say root.write. So 6, which has been called by 5.write, right? And then 6 comes in. 6 is not null. First call for 6 would be 6.left, which is null, called by 6.left. And then 6.left is going to return 0. So now we have 0. Let's also remember the previous result. 2 plus 1. We have 0, comma. Now we trace back to 6 again, and we call 6.write. There's no 6.write, so we get null in the function. We again return 0, so we set it to 0, and then we add 1 to it and return it. Trace back to 5, because 5 was the original caller, which led us to 6. 5. This condition for 5 has already checked. We had paused our execution at this step, so we have gotten our right result, which is 1. And then the previous result was 3. So we're going to end up, let's complete the 5 here. 5 is going to be 1 plus 1. So the original caller is going to get max of 2, comma, the previous result was 2 plus 1, 3. We're going to get back 3, right? Which is nothing but 3. So the external caller of max step is going to get 3. So this is how you would walk through a binary search tree or a binary tree in an interview setting when you already have the code written. Right. So now let's get to the space and time complexity here. The space complexity is going to be big O of n, where n is the number of nodes in the tree, because we are traversing through the tree and trying to visit all the nodes once. So it's going to be big O of n. And why the big O of n? Because the depth or the size of our recursive call stack is going to be n elements long, so right, which is nothing but size of our recursive call stack. There are going to be n function instances spawned up by the very first call, right? And the time here is going to be big O of n, where n is the number of nodes in the tree. And as I mentioned, it's big O of n because we're going to traverse n nodes, traverse through the tree and visit n nodes, and it's going to give us big O of n. Well, that was about how we use depth first search to find the max depth in a binary tree. I'll see you in the next one with a new question, and which would again cover how we can utilize DFS pattern to solve more interesting questions. Thank you so much. See you in the next one. Bye.